floating in the frozen void 1 million miles from our planet, a machine the size of a tennis court has detected something extraordinary. The James Webb Space Telescope has found what scientists are calling Earth 3.0, a world wrapped in clouds, bathed in water, surrounded by an atmosphere that defies explanation unless something living breathes beneath those alien skies. But the discovery goes deeper than anyone anticipated. Hidden within the data streams flowing back from this distant world are signatures, patterns that emerge and repeat with a precision that natural forces cannot create. Someone is already there, and whatever intelligence calls that world home appears to know we're observing them. If you're drawn to exploring cosmic mysteries with us here at Late Space, take a moment to subscribe and leave us a like. Your support allows us to continue bringing these contemplative journeys through the universe to you. Now let's venture together into this profound discovery. Understanding why this finding shakes the foundation of human knowledge requires returning to the beginning. Not the universe's origin, though we'll touch on that eventually, but rather to a question that has haunted our species since the first humans gazed skyward and wondered whether those distant lights might be other suns harbouring other worlds and other lives. Are we the only ones? Throughout most of human existence, this question belonged to philosophy and faith rather than science. The stars hung too far away. The cosmos stretched too wide. No instrument we possessed could reach across that vast ocean of space to discover what awaited on distant shores. That reality shifted gradually, then suddenly. Every civilization Earth has produced looked toward the heavens and imagined possibilities. Ancient cultures projected gods and ancestors onto stellar patterns. Medieval thinkers debated whether the celestial spheres might contain inhabited realms. Renaissance scholars, emboldened by Copernicus's revolutionary model, began suspecting our sun represented merely one among countless others, each potentially circled by their own Earths. The 20th century brought scientific rigour to the question. Astronomers confirmed the stars were indeed distant suns, some massive, others small, but fundamentally similar to our own. They discovered our galaxy contained hundreds of billions of stars, and the observable universe held hundreds of billions of galaxies. The mathematics proved staggering. How could consciousness exist in only one location within such incomprehensible vastness? Yet we possessed no evidence either direction. Distances stretched too far. Technologies remained too primitive. We could speculate and calculate probabilities, but certainty eluded us. The question persisted as existence's greatest enigma. Radio astronomers aimed their instruments toward the stars, searching for artificial transmissions. They heard only cosmic static. Space probes visited every planet circling our sun and discovered no signs of intelligence. Mars, once imagined as harbouring advanced civilizations, revealed itself as a frozen wasteland. The cosmos seemed stubbornly silent. Some researchers began wondering whether we truly existed alone. Perhaps life emerged more rarely than our optimism suggested. Perhaps intelligence represented a singular accident occurring only here on this small world, in this unremarkable corner of everything. Perhaps the cosmic silence conveyed a message we resisted hearing. Others refused that conclusion. They indicated the universe's immensity, the billions of years available for evolution, the fundamental chemistry apparently favouring biological systems. Absence of evidence, they insisted, differs from evidence of absence. We simply required better instruments. The story of how we arrived here, how we constructed a machine capable of discovering Earth 3.0, chronicles human determination, brilliant engineering, and decades of labour by thousands who refused accepting that some questions exceeded our capacity to answer. The James Webb Space Telescope didn't materialise overnight. Its origins trace to 1989, merely 3 years after Hubble launched and transformed our cosmic perspective. Even as Hubble revealed nebular beauty and galactic depths, scientists already envisioned something larger, something superior, something capable of observing not just visible light, but the invisible radiation carrying secrets from time's beginning. The universe bathes in light our eyes cannot perceive. Infrared light, heat itself. This represents the cosmos's language, how the universe whispers its profoundest secrets. Stars forming within gas and dust clouds speak through infrared. Ancient galaxies at the observable universe's edge have had their light stretched by spatial expansion until it glows solely in infrared wavelengths, and planets orbiting distant stars, worlds potentially harboring life, reveal their secrets through faint infrared atmospheric signatures. Hearing these whispers demanded a new telescope, Variety, one collecting infrared light with unprecedented sensitivity, one seeing farther and clearer than anything humanity had constructed, one functioning flawlessly millions of miles from Earth, in the cold darkness between our world and the Sun. The challenges proved formidable. Infrared telescopes face problems optical telescopes avoid. They detect heat, and everything radiates heat. Your body, your devices, your room's walls, the telescope itself. Detecting a distant planet's faint infrared glow requires your telescope achieving extreme cold, remarkably cold, colder than anything terrestrial. James Webb was designed operating below -400 degrees Fahrenheit. At such temperatures, instruments become sensitive enough detecting a bee's warmth on the moon. Achieving that cold in space required solving unprecedented engineering problems. The solution emerged both elegant and audacious. Webb would carry a sun shield matching a tennis court's dimensions, constructed from 5 Kapton layers, each thinner than human hair. This shield would block solar heat, allowing the telescope cooling to necessary operating temperatures. But the shield exceeded any rocket's capacity. It required folding like origami, launching into space, then autonomously unfolding millions of miles from any assistance. The primary mirror presented additional challenges. Collecting sufficient light for observing the universe's faintest objects demanded a huge mirror, 21 feet across, far exceeding any rocket's capacity as a single piece. Engineers designed it as 18 hexagonal segments, each coated with atomically thin gold layers. Gold excellently reflects infrared light. The segments would fold for launch, then unfold in space, aligning themselves with nanometer precision. 1 nanometer equals 1/1000th of a meter. For comparison, human hair measures roughly 80,000 nanometers wide. Year after year, Webb's team solved problem after problem. They invented new technologies. They exhaustively tested every component. They prepared for every imaginable failure mode and many beyond imagination. The original 2007 launch date slipped, then slipped again. Budget problems emerged. Political battles threatened cancelling the entire project, but the dream persisted. The telescope represented too much importance. The questions it might answer carried too much weight, so work continued through 2 decades of setbacks and breakthroughs, through economic crises and political shifts, through dedication from scientists and engineers who devoted careers to building something potentially reshaping humanity's cosmic understanding. Christmas morning 2021 saw James Webb finally departing Earth. It rode skyward on an Ariane 5 rocket launched from French Guiana on South America's northern coast. Controllers held their breath as the rocket carried its precious cargo away from our world. No rescue mission could occur, no repair crew existed. If anything failed, 2 decades of work and $10 billion would vanish forever. Nothing failed. Rather, nothing failed that teams hadn't prepared for. The launch proved so precise that Webb retained extra fuel, extending its potential mission lifetime far beyond the original decade-long plan. The sun shield deployed perfectly, all 5 layers separating and stretching taut. The primary mirror unfolded, all 18 segments clicking into position like a golden flower blooming in the void. Webb travelled 1 month, reaching its destination, a special location called the second Lagrange point, or L2. This represents a gravitational balance point approximately 1 million miles from Earth on the Sun's opposite side. At L2, the telescope maintains its sunshield pointed toward the Sun, while its instruments face deep space's dark cold, perpetually ready receiving faint light from distant worlds. Webb's first images stunned the world. Galaxies older than any previously observed, their light having journeyed over 13 billion years reaching us. Stellar nurseries where new stars formed, their swirling gas and dust clouds revealed in stunning detail. An exoplanet's atmosphere analysed with sufficient precision, identifying individual molecules in alien air. These images made worldwide headlines. They demonstrated the decades of work and billions of dollars proved worthwhile. Webb performed beyond specifications in nearly every category. The universe opened before us as never before. At research centres and universities across the planet, scientists pored over the data. Each image contained more information than any individual could analyse. Teams divided this work, each focusing on their expertise area. Cosmologists studied distant galaxies. Star formation experts examined stellar nurseries. Planetary scientists analysed exoplanet atmospheres. The public watched with wonder mixed with impatience. The images proved beautiful, but where were the aliens? After all the anticipation, all the promises about Webb's capabilities, people wanted knowing. Were we alone? Scientists counselled patience. Discovering life signs, if they existed, would require time. Data needed careful collection, rigorous analysis, checking and rechecking. Science couldn't be rushed. The universe had waited 13 billion years for understanding. Several more months or years wouldn't matter. But even scientists privately admitted hoping for something more. They dedicated careers to understanding the cosmos. They knew the odds. They knew habitable planets might prove common, that life might arise wherever conditions permitted. They dared hoping their generation would make the ultimate discovery. Webb functioned better than anyone dared hope, and it was about to find something changing everything. Earth 3.0's discovery didn't happen in one dramatic moment. Science rarely functions that way. It emerged through patient data accumulation, through observations seeming routine until suddenly they weren't. The target was a star designated Kepler 442, a K-type dwarf star located approximately 1,120 light-years from Earth in constellation Lyra. This star had interested astronomers for years because Kepler Space Telescope, Webb's predecessor, had detected an orbiting planet. Kepler 442b, as designated, sat in the habitable zone, that sweet spot around a star where temperatures might permit liquid surface water. But Kepler could only reveal the planet existed and roughly its size. It couldn't determine what kind of world it truly was, rocky like Earth, gaseous like Neptune, ocean-covered or barren as Mars. Those questions required a different approach. They required examining the planet's atmosphere. When a planet passes before its star from our perspective, tiny starlight fractions filter through the planet's atmosphere before reaching us. Different molecules absorb different light wavelengths. Analysing which wavelengths are missing or weakened allows scientists determining what gases exist in alien skies. This technique, called transmission spectroscopy, represents one of Webb's greatest strengths. Kepler 442b observations began as part of a larger survey. Webb was scheduled studying dozens of potentially habitable worlds, building a picture of how common Earth-like atmospheres might prove. Nobody expected any single observation producing earth-shaking results. The universe, after all, is vast, and we'd examined many worlds without finding clear life signs. The first data showed something intriguing: water vapour, abundant water vapour, exceeding model predictions for that planet size. The research team noted it as interesting and scheduled follow-up observations. Water proves necessary for life as we know it, but doesn't prove life exists. Many dead worlds contain water. The second dataset showed something else: oxygen. Not trace amounts, but substantial quantities, enough suggesting active processes replenishing the atmosphere. On Earth, our oxygen comes primarily from photosynthesis. Plants and cyanobacteria constantly pump it out. Without them, our oxygen would slowly react with other elements and disappear. Now the team paid attention. Water and oxygen together proved a powerful combination. Still not proof, but suggestive. They requested priority observation time. Webb turned its full attention to this one small world orbiting a distant star. The third dataset changed everything. Hidden in the atmospheric signature, barely visible above noise, existed something that shouldn't be there: methane. Significant methane amounts coexisting with significant oxygen amounts. Understanding why this matters requires understanding some chemistry. Methane and oxygen don't like each other. When they meet, they react. The methane combines with oxygen, and both are destroyed. On planetary scales, this reaction happens relatively quickly in geological terms. If you have abundant quantities of both gases in an atmosphere, something must constantly produce them. On Earth, that something is life. Cattle produce methane. Termites produce methane. Bacteria in swamps and ocean floors produce methane. Meanwhile, plants and algae produce oxygen. The two gases exist in constant conflict, constantly being replenished by living things. Finding both gases together in Kepler 442b's atmosphere was like finding smoke without fire. The smoke shouldn't persist unless something keeps generating it. The simplest explanation, requiring the fewest assumptions, was that this planet possessed an active biosphere, living things, alien life. But the team exercised caution. Science demands skepticism of extraordinary claims. False alarms had occurred before. Mars had seemed showing methane signs that proved measurement errors or unusual chemistry. They needed ruling out non-biological explanations before stating what they suspected. Could volcanoes produce the methane? They ran calculations. The volcanic activity required producing that much methane would also produce other gases that weren't present. The volcanic explanation didn't fit. Could photochemistry in the upper atmosphere explain it? They modelled the chemistry. The models couldn't reproduce observed ratios without some unknown process. Could exotic geological processes they hadn't considered exist? They consulted experts from every relevant field. Nobody could offer a non-biological explanation fitting all the data. Weeks turned into months as the team double-checked everything. They reanalyzed raw data. They recalibrated instruments. They ran observations again and got identical results. Whatever was producing methane and oxygen on Kepler 442b was doing it continuously and substantially. The preliminary paper was drafted and redrafted. Conclusions were stated carefully with all appropriate caveats. Science doesn't deal in certainty, only probabilities. But the probability that something was alive on this distant world was high enough that the team felt comfortable stating what they'd found. Kepler 442b showed strong biological activity evidence. The planet wasn't just potentially habitable. Something was actually living there. The news spread through the astronomical community like wildfire. Other observatories pointed their instruments at the star. Independent teams confirmed the atmospheric readings. The data was solid. The chemistry was clear. Unless our atmospheric science understanding was fundamentally wrong, Kepler 442b harbored life. But that was only the story's beginning. Because as astronomers continued watching and analysing, they found something else. Something transforming an already historic discovery into something far more profound and far more unsettling. The follow-up observations required patience. Webb had many demands on its time, and the team had to wait their turn in the observation queue. But when their window came, they maximised it. They observed Kepler 442b for hours at a stretch, gathering as much data as the telescope could collect. The infrared sensors proved key. These instruments could detect heat with extraordinary precision, measuring temperature differences of just fractions of degrees from 1,120 light-years away. The data they produced was essentially a heat map of the planet showing which areas were warmer and which were cooler. The initial analysis was straightforward. The planet's day side was warmer than its night side, as expected. The equator was warmer than the poles. There were variations corresponding to what might be continents and oceans, with water holding heat differently than land. But then anomalies started appearing. The infrared data from Kepler 442b showed thermal patterns on the planet's surface, hot spots and cold spots changing over time as the planet rotated. This was expected. Any world with an atmosphere would have weather, temperature variations, differences between day and night. But the patterns were strange. Some hotspots appeared where they shouldn't be. Areas that, based on the planet's geography and starlight angles, should have been cool were radiating excess heat. The differences were small but measurable. They were also regular. The hotspots appeared and disappeared in cycles, not the cycles of days or seasons, but shorter cycles repeating with almost mechanical precision. One researcher working late at night going through the data made an observation she almost dismissed as impossible. The hotspots weren't random. They were clustered, and the clusters formed shapes. She ran the analysis repeatedly. The shapes persisted. They weren't natural formations. They were too regular, too geometric, too obviously designed. Something down there had been produced by intelligent design. Those were the words she wrote in her notes, words that would later become famous. At the time, she didn't share them with anyone. The claim was too extraordinary. She needed more evidence. Over following weeks, she gathered it. The thermal patterns showed clear structure signs, straight lines where no geological process could produce them, grid patterns, heat concentrations suggesting not volcanism but industry, warmth being produced and released in ways matching activity rhythms rather than geology. The analysis expanded, more researchers were brought in, computer algorithms were set to work finding data patterns. The conclusion became inescapable. Kepler 442b didn't just have life, it had civilization. The term Earth 3.0 emerged from early discussions among the research team. It wasn't meant as a formal designation, just shorthand for what they were seeing, a world with water, oxygen, methane and technological activity signs. A world that had apparently followed a path similar to ours, developing not just biology but intelligence and industry. Earth 1.0 was our own planet, the original. Earth 2.0 had been a term used for various planets physically resembling ours, but showing no life signs. Earth 3.0 was something new. A world not just habitable, but inhabited, not just alive, but awake. The implications proved staggering. For all human history, we'd wondered if we were alone. Now we had evidence we weren't. Somewhere out there around a star we could see in our night sky, beings were living their lives, going about their business, completely unaware that a small blue world called Earth had just discovered them. Or were they unaware? As analysis continued, something became clear that added another complexity layer to an already complex situation. The thermal patterns weren't static. They were changing. Not just in cycles of what might be daily or weekly activity, but changing in response to our observations. This sounds impossible, so let me explain carefully. The James Webb Space Telescope is essentially passive. It collects light. It doesn't send signals to observed objects. There's no way for anything on Kepler 442b to know it's being watched, at least not through any Webb detection. But we're not the only ones who build telescopes. If a civilization exists on Kepler 442b, they might have their own instruments pointed skyward. They might have noticed our star, Sol, and wondered about it, just as we wondered about theirs. They might have built their own astronomical tools capable of detecting technology signs in atmospheres of planets orbiting distant stars. Our planet, after all, has been broadcasting its presence for over a century. Radio waves from our communications have been spreading outward at light speed since the early 20th century. Our atmosphere is rich with industrial chemicals any sufficiently advanced civilization could detect. City lights on our night side glow brightly in thermal imaging. Kepler 442b is 1,120 light-years away. That means light, including radio waves, takes 1,120 years travelling between our worlds. Any signals we send today wouldn't arrive there until more than a millennium from now. Any signals they sent today wouldn't arrive here for just as long. But here's the thing, we've been here a long time. Our technological civilization has been visible in principle for over a century. If they detected us 50 years ago, they might have decided doing something about it, something requiring time to implement, something becoming visible to us only when enough time had passed. The thermal patterns the research team was observing included structures appearing new, developments seeming recent, construction, if that's what it was, that had occurred within the last few years of observational data. Coincidence? Perhaps. We can't know for certain, but the timing was suggestive. It was as if upon learning another civilization existed in the cosmos, they had decided, building something in response, something visible, something meant to be seen. The researchers debated endlessly about what this might mean. Were they trying to communicate? Were they showing off their capabilities? Were they sending a warning? Or was it all unrelated to us? The activities of an alien civilization going about its own business for its own reasons. The only thing everyone agreed on was that the discovery raised more questions than it answered. We had found that we weren't alone. We had found that the universe contained other minds, other lives, other civilizations. But we had no idea what they wanted, what they thought, or how they might respond to our discovery of them. And so humanity stood at a threshold. Behind us lay all of history, all the millennia of wondering and dreaming and fearing what might be out there. Ahead lay an unknown future shaped by a discovery that would force us reconsidering everything we thought we knew about our place in the cosmos. The discovery of Earth 3.0 wasn't just a scientific achievement, it was an existential event, the kind of moment coming perhaps once in a species' history, the moment when you learn you're not alone. Let us take time understanding this planet, this Earth 3.0, in more detail. What do we actually know about Kepler 442b, and what can we infer from the data? The basics are well established. The planet orbits its star at roughly 0.4 astronomical units, about 37 million miles, completing one orbit every 112.3 Earth days. This places it firmly in the habitable zone of its star. Kepler 442 deserves attention. Kepler 442 is what astronomers call a K-type main sequence star, also known as an orange dwarf. It's about 61% as massive as our Sun, and roughly 35% as luminous. Stars like this are extremely common in the galaxy, far more common than Sun-like G-type stars. If life and civilization can arise around K-type stars, then potential intelligence homes in our galaxy increase dramatically. K-type stars also live longer than our Sun, much longer. While our Sun will exhaust its fuel in approximately 5 billion years, K-type stars can burn steadily for 15 to 30 billion years. This gives life more time to evolve and civilizations more time to develop. The beings of Kepler 442b might have existed longer than life has existed on Earth. They might possess history depths we cannot fathom. Or they might be younger than us. We can't tell from our available data. A civilization's age isn't written in its thermal signatures. We see what they are, not when they began. The planet itself is approximately 1.34 times Earth's diameter, making it what astronomers call a super-Earth. Its mass is harder determining precisely, but estimates suggest roughly 2.3 times as massive as our world. This would give its surface gravity about 1.28 times Earth normal, not uncomfortable for human visitors, though we would feel noticeably heavier. The term super-Earth might sound dramatic, but it simply refers to planets larger than Earth but smaller than Neptune. Many super-Earths have been discovered, and they appear among the most common planet types in the galaxy. Finding a habitable super-Earth with life signs suggests such worlds might prove even more hospitable to civilization development than Earth-sized planets. Why might larger planets be better for life? Several reasons have been proposed. Larger planets can hold thicker atmospheres, providing better radiation protection and better temperature regulation. They have stronger magnetic fields deflecting harmful stellar particles. They have more geological activity recycling nutrients and regulating atmospheric composition over long timescales. Of course, planets can also be too large. Giant planets like Jupiter and Saturn have crushing gravity and no solid surface. The sweet spot for life appears in the super-Earth range, large enough having sizes benefits but not so large as becoming a gas giant. Kepler 442b falls right in this sweet spot. The atmosphere appears primarily nitrogen, like Earth's, with significant oxygen amounts, water vapour, and trace gases including methane and carbon dioxide. The proportions differ from our atmosphere, but not wildly so. An unprotected human on the surface couldn't breathe the air directly, but it wouldn't be immediately toxic either. With proper filtration and oxygen supplementation, survival would be possible. Surface temperature varies with location and time of day, but averages in the range comfortable for life as we know it. The thermal data suggests large liquid water bodies, almost certainly oceans. The planet appears having both polar and tropical regions with weather patterns suggesting active atmospheric circulation. All this would be remarkable enough for any newly discovered exoplanet. Finding a world so similar to Earth at all was a major achievement, but the technology signs transformed this from an important discovery into a historic one. The thermal signatures consistent with industrial activity are concentrated in several planetary surface locations based on their appearance and disappearance timing as the planet rotates. Researchers have mapped out approximately where these regions are. The highest concentrations appear on a landmass in the southern hemisphere and along a large northern hemisphere continent's coast. The pattern suggests cities, large urban areas generating heat through daily activity cycles, brighter at certain times and dimmer at others. The regularity of patterns implies organization, infrastructure, routines, civilization. Beyond the cities there appear to be other structures, linear features connecting urban areas, possibly transportation networks, scattered hotspots that could be factories or power plants, agricultural regions showing different thermal signatures than wildlands. All this is interpretation, of course. We're inferring a great deal from limited data. The thermal resolution we can achieve from this distance is measured in hundreds of miles. We cannot see individual buildings or vehicles. We cannot read their signs or watch their people. We can only see a technological civilization's gross thermal output and try making sense of the patterns. But the patterns are there unmistakably. The longer we look, the more details emerge, and the more details emerge, the clearer it becomes we're looking at something real. A civilization, a people, beings going about their lives on a world 1,120 light years from our own. Who are they? What do they look like? What do they think? What do they want? These are questions we cannot answer with current technology. The distances involved are simply too vast. Even our best telescopes can only see them as heat patterns on a distant world. But we can speculate. We can consider what their world's conditions would have produced, and what kind of beings might have evolved there. The surface gravity is higher than Earth's, suggesting life forms there might be more compact, more powerfully built, adapted to moving under greater gravitational stress, but not dramatically different. The difference between their gravity and ours is similar to the difference between living at sea level and living in mountains. The atmosphere has a higher oxygen proportion than ours, which could support more active metabolisms. Creatures might be able sustaining higher activity levels. Alternatively, life forms might have evolved using that oxygen more efficiently, with tissues resisting oxidative damage better than ours. The star they orbit is cooler and redder than our Sun. Plants on their world, if they have plants, would likely be darker in colour, optimized absorbing the wavelengths their star produces most abundantly. Their sky might appear a different colour than ours, the familiar blue replaced by something more amber or even deep red. Beyond these broad speculations, everything is uncertain. Evolution is opportunistic. It produces whatever works, not whatever makes sense to outside observers. The beings of Kepler 442b might be humanoid, or they might be something we could barely recognize as alive. They might have senses we lack or lack senses we take for granted. Their thoughts might be comprehensible to us or utterly alien. What we can say with some confidence is that they're technological. They've built things. They've altered their environment in ways visible from over 1,000 light-years away. This suggests certain commonalities with humanity, at least in capabilities terms. To develop technology, you need appendages capable of manipulating the physical world with precision. You need a nervous system complex enough supporting abstract thought, planning, and communication. You need a social structure allowing knowledge accumulation and transmission between generations. You need curiosity, the drive to understand and control your environment. In these ways at least, the beings of Kepler 442b must be like us. Different in countless details, no doubt. Products of separate evolutionary history on a separate world under a separate star, but recognizably similar in their fundamental relationship to the universe. Minds that wonder, hands that build, civilizations that grow. And that brings us to the most profound question raised by this discovery. What does it mean for us? How should humanity respond to the knowledge that we're not alone? The debate began even before the research was made public. The team that analysed the data argued about whether to release it at all. Some felt the implications were too significant, that world governments should be consulted before announcement. Others argued that science had to be open, that hiding such a discovery would betray everything research stood for. In the end, the decision was made to publish. The paper appeared in a leading scientific journal, peer-reviewed and vetted through normal channels. The announcement was made at a press conference drawing every major news organisation worldwide. The reaction was everything you might expect and more: joy, fear, wonder, denial. Religious leaders scrambled reconciling the discovery with their doctrines. Political leaders issued statements ranging from cautious optimism to apocalyptic warning. Stock markets briefly panicked before stabilizing. Social media exploded with speculation, memes, conspiracy theories, and genuine awe. Some people celebrated. For them, confirmation that we weren't alone was the answer to a lifelong hope. The universe was alive, teeming with intelligence, full of possibilities we were only beginning to imagine. Others feared. The history of encounters between civilizations on Earth offered little comfort. When two cultures met and one was technologically superior, the results for the lesser civilization were often catastrophic. Were we the lesser civilization now? Were we in danger from beings we couldn't understand and couldn't resist? Still, others simply couldn't accept the news. They had built their worldviews around human uniqueness, and this discovery shattered that foundation. They called the findings faked, the data manipulated, the conclusions premature, and many, perhaps most, simply went about their lives. The beings of Kepler 442b were very far away. Whatever they were doing over there had no immediate impact on daily concerns here. Rent was still due. Children still needed feeding. Jobs still demanded attention. Life continued even as the universe revealed itself stranger and more populated than anyone had known. But even those who set the news aside and focused on daily life had been changed by it. The sky looked different now. Those stars weren't just light points anymore. They were potential homes, possible civilizations, distant neighbours in a cosmic community we were only beginning to discover. The philosophical implications ran deep. For centuries, thinkers had debated whether intelligence was common or rare in the universe. Some argued life's conditions were so specific, the evolutionary path to intelligence so narrow that we might be alone in the cosmos. Others contended life would arise wherever conditions permitted, that intelligence was an inevitable consequence of biological evolution, that the universe must be teeming with minds. The discovery of Earth 3.0 didn't settle the debate entirely, but it shifted the odds dramatically. One data point isn't conclusive, but it isn't nothing either. If we found technological civilization around the very first habitable planet we looked at carefully, that suggested such civilizations might be common, the universe might be full of them, waiting to be discovered, and if civilizations were common, why hadn't we heard from them before? This was the essence of the famous Fermi paradox, named after physicist Enrico Fermi, who reportedly asked, "Where is everybody?" If intelligent life was common in the galaxy, why wasn't the galaxy obviously full of it? Why hadn't we received clear signals, been visited by explorers, found artifacts of ancient civilizations? The discovery of Kepler 442b suggested one possible answer. Perhaps civilizations were common, but communication was rare. 1,120 light-years meant any message exchange would take 2,240 years for a question and answer. Perhaps civilizations simply waited in their own solar systems, aware of each other but not communicating, separated by the vast and silent spaces between stars. Or perhaps civilizations communicated in ways we couldn't yet detect. Perhaps they had moved beyond radio waves to technologies we hadn't invented. Perhaps the galaxy was buzzing with conversation, and we simply didn't have the equipment hearing it. Or perhaps, most troublingly, there was something preventing civilizations from expanding beyond their homeworlds, something that stopped them, destroyed them, or changed them into something no longer wanting to explore. The Great Filter, some called it. A barrier few or no civilizations managed to pass. Were we past the filter or approaching it? Was our future bright with discovery and expansion? Or was there something ahead that would end our journey before it truly began? The beings of Kepler 442b had apparently survived long enough building a visible civilization. Did that mean they had passed their filter? Or were they like us, still approaching it? These questions had no clear answers. They might never have clear answers. But the discovery forced us confronting them in ways that had previously been merely theoretical. The questions were real now. The stakes were real. The universe was alive with intelligence, and we had to figure out what that meant for us. The cultural response to the discovery was as varied as human culture itself. Artists, writers, musicians, and filmmakers found in it an endless inspiration source. Within months of the announcement, galleries filled with works imagining life on Kepler 442b. Novels were written exploring contact's implications. Music captured the awe and terror and wonder the discovery evoked. Some of this art was optimistic, depicting futures where humanity and the beings of Kepler 442b became partners exploring the cosmos. Others were darker, imagining conflicts and catastrophes contact might bring. Still others were simply meditative, trying to capture the profound strangeness of knowing we weren't alone. The philosophical response was equally varied. Existentialist thinkers argued the discovery made human existence more meaningful, not less. We were part of something larger, participants in a cosmic drama giving our brief lives significance. The fact others existed didn't diminish us. It connected us to a universe that would otherwise have been empty and meaningless. Others took the opposite view. If intelligence was common, then humanity wasn't special. We were one civilization among many, perhaps countless. Our achievements, which had seemed so remarkable when we thought we were alone, were simply typical accomplishments of a typical species on a typical planet. Pride in human uniqueness was no longer justified. Still others argued the meaning question was unchanged by the discovery. Meaning came from within, from the values and purposes individuals and societies created for themselves. Whether the universe contained one intelligence or a billion, that fundamental truth remained the same. The academic world mobilized studying every discovery aspect. New departments and institutes were established at universities worldwide. Funding poured into fields that had previously struggled for recognition: astrobiology, xenolinguistics, comparative planetology, and a dozen other disciplines emerged or expanded. Young people flocked to these fields, inspired by the discovery and eager contributing to the story's next chapter. The best minds of a generation turned their attention to questions that had once seemed purely speculative. What is alien intelligence's nature? How might communication be established? What are technology's limits? What is civilization's ultimate fate? These questions would occupy humanity for generations. But they were no longer merely theoretical. They were practical questions with real stakes and real consequences. The discovery had transformed inquiry's nature itself. In months following the announcement, the world began adjusting. The immediate shock faded into a kind of new normal. The beings of Kepler 442b became a topic of casual conversation, something people discussed at parties and debated on forums. Scientific institutions reorganized their priorities. The search for extraterrestrial intelligence, once a somewhat fringe pursuit, became a central astronomy focus. New instruments were proposed and funded. International cooperation increased as nations recognized this was a challenge too big for any one country addressing alone. Plans began forming for how humanity might respond. Should we send a message? If so, what should it say? Who should speak for Earth? How could we represent human civilization's diversity to beings knowing nothing about us? These questions were complicated by the time delay. Any message we sent would take 1,120 years arriving. Any response would take another 1,120 years returning. The people who sent a message wouldn't live receiving an answer. Their great-great-great-grandchildren's great-great-great-grandchildren might not live receiving an answer. This was communication across generations, across centuries. It required a kind of patience and long-term thinking human institutions weren't designed for. It required us acting not for ourselves, but for our descendants, trusting they would continue what we started. Some argued we shouldn't send a message at all. The beings of Kepler 442b knew we were here. Our civilization had been broadcasting its presence for over a century, but we hadn't deliberately attracted their attention, not yet. Perhaps we should wait, watch, learn more before making direct contact. Others argued silence was itself a kind of message, that refusing to respond would seem fearful or hostile, that if we wanted peaceful relations with our cosmic neighbours, we should extend a hand in friendship as soon as possible. The debate continued without resolution. Different factions advocated different approaches. The United Nations established a committee studying the question, which issued reports and recommendations promptly ignored by national governments pursuing their own agendas. Private organisations announced plans sending their own messages, claiming they didn't need official permission speaking to the stars. Meanwhile, observations continued. Webb and other telescopes kept their eyes on Kepler 442b, gathering more data, refining our understanding. The thermal patterns continued evolving. The industrial activity signs continued spreading. Whatever was happening on that distant world was ongoing, dynamic, alive. And then approximately 18 months after the initial discovery, something new appeared. The observers weren't expecting it. By this point, Kepler 442b had become a routine target. Teams took turns monitoring the data stream, looking for gradual thermal pattern changes, hoping to understand more about alien industry's rhythms. They expected slow evolution, the kind of change happening over years or decades as a civilization grows and develops. What they got was something else entirely. The thermal sensors detected a sudden intense heat burst from the planet's surface. Not a gradual change like patterns observed before, a spike, a flash, an event. The alert went out immediately. Researchers worldwide dropped what they were doing and rushed analysing the incoming data. Something was happening on Kepler 442b. Something big, something unprecedented in all their observations. The burst lasted several hours, then faded. Data analysis suggested something extraordinary. The energy release was consistent with a massive nuclear detonation, but the pattern was wrong for a weapon. It was too concentrated, too directed. It looked less like a bomb and more like a rocket engine. The implications hit the research community like a thunderbolt. If this was a launch, it meant the beings of Kepler 442b had spaceflight capability. More than that, it meant they had propulsion technology far beyond anything humanity possessed. The energy signature suggested velocities our rockets could never achieve. They weren't just a technological civilization, they were an advanced technological civilization. Some researchers hoped it was just a test, an experiment, a probe sent into orbit or toward one of their own moons. That would be remarkable enough, but wouldn't necessarily concern us directly. Those hopes were dashed over following weeks. Tracking data revealed that something had left Kepler 442b. Something small. Too small seeing directly, but its trajectory could be inferred from gravitational effects on dust and debris in its path. Something was moving away from the planet, accelerating to a significant fraction of light speed. The trajectory was clear, unmistakable. The object wasn't heading toward any other body in the Kepler 442 system, it was heading toward us, toward Sol, toward Earth. They had launched something into space. The timing was impossible to ignore. The launch came roughly 1,120 years after the first human radio signals could have reached Kepler 442b, allowing for detection time, analysis time, decision time, and construction time. The sequence made sense. They had heard us. They had decided to respond. And their response was not a message, but a probe, or perhaps a ship. We have no way knowing yet what they sent. The object is too small and too far away observing directly. We can only see its effects on its environment, the subtle perturbations in light and dust revealing something is there and moving. If it maintains its current trajectory and speed, it will reach our solar system in approximately 1,000 years. That's an estimate with significant uncertainty. The object could accelerate further, could change course, could be something completely different from what we assume. But the best current guess is that something from Kepler 442b will arrive in our neighbourhood within the next millennium. This changes everything. Again. The discovery of intelligent life was profound. The discovery that they're sending something toward us is something else entirely. We're no longer passive observers. We're participants in an unfolding contact between civilizations. What should we do? How should we prepare? These questions have occupied governments, militaries, scientists, and ordinary citizens since the launch was detected. The answers depend enormously on what the object turns out to be. If it's an automated probe similar to the Voyager spacecraft we sent out decades ago, then the main challenge is communication. The probe will likely carry some attempt establishing common ground, mathematical concepts or physical constants any technological civilization would recognize. We would need decoding its messages and formulating responses. If it's a crude vessel, the challenges multiply. How do we meet beings who've spent a millennium traveling through space? What condition will they be in? What do they expect from us? How do we avoid misunderstandings that could escalate into conflict? If it's something else entirely, a weapon, a seed ship, a technological artifact beyond our comprehension, then we're in territory where no planning can help. We would simply have to respond to whatever arrived. The uncertainty is maddening. We know something is coming, but not what. We know roughly when, but not precisely. We have perhaps a millennium to prepare, which sounds like a long time, but isn't. Human institutions think in terms of years, not centuries. The people making decisions today won't be alive seeing the consequences, and yet preparations are underway, quietly in research facilities and government agencies around the world. Plans are being made, protocols are being drafted, technologies are being developed. Humanity is doing what it has always done when faced with the unknown. It's trying to understand, trying to prepare, trying to survive. The mood among those knowing the details is complicated. There's excitement at the prospect of meeting another civilization. There's fear of what that meeting might bring. There's awe at the scale of what's happening, and there's a strange kind of peace. the acceptance that some things are simply beyond our control. We didn't choose this moment. We didn't choose to be the generation discovering we weren't alone, but we are that generation. The discovery has been made. The object is on its way. Whatever happens next, nothing will ever be the same. And so we wait. We watch. We wonder. The same three things humanity has always done when confronting the infinite mysteries of the cosmos. But now the mysteries are watching back. Now the cosmos contains not just stars and planets, but minds like ours. Possibly friends, possibly rivals, possibly something we cannot yet imagine. The James Webb Space Telescope continues its observations. Every day more data arrives, more details emerge. The picture of Kepler 442b becomes clearer even as the questions it raises multiply. And somewhere in the void between our worlds, something is coming. This is where we are. This is the moment we inhabit. The most significant discovery in human history has been made, and its full implications will unfold over generations. We are the beginning of something vast. We are the first to know that we're not alone, and whatever comes next, that knowledge will never leave us. We will carry it forward into whatever future awaits. We will be different because of it. We already are. The story of Earth 3.0 is just beginning.